So let's look at the second example problem. No, this is not 2020. This is IOI 2010 problem. So I find it through this user code guide page. It's actually a relatively easy problem, relative standard problem. So I guess IOI they have a very difficulty to make sure that for each participant they will be able to solve some of the problems. So this is one of the standard ones. So the problem is describing a setting of cities. So for each city, we have a number of people, number of hockey fans, and we're trying to pick a city to build a stadium. And what happens is everyone will go to this city to watch the game. And when the game is over, everyone who do not live in this city will try to leave. So then, for example, here, we have 20 people live in this city, 20 live in this city. Then we'll have 40 people trying to leave on this, travel on this edge. So we want to minimize this maximum range. So for example, if we pick this city as the where we build the stadium, then this number will be 40. So we have 10 people living here, 10 people here, and the 40 people living this. So this congestion value will be 40. On the other hand, if we pick here, then we will have 30 people going here, so 10 plus 10 plus 10, and then 20 people from here. So then the maximum congestion is 30. I think this is probably the best, yes. So so then we should pick this city. So the question asks us to pick this best city. So then to formulate the way the problem is formulated is essentially we want to pick a node to root the tree, and then obviously once we pick a node at the root, then the busiest edge will be from this root to one of the subtrees. So then if we pick this, there are 3 subtrees, their total weight is 10, 10, and 40. So then this 40 become this value. So we are essentially want to pick a node so that when we root the tree at that node, the maximum size of the subtree is minimized, and the size is a total sum of the weight. So each node will have a different weight. We're not just counting the number of nodes. So that's what this problem is about. So yeah, find a node so that when the tree is rooted at that node, the maximum weight of each subtree of the root node is minimized. So encourage you to pause the video, try to solve the problem. So the problem description have different subtasks. There are 4 different subtasks. Essentially, the earlier ones allow you to use a less efficient algorithm and still pass. But the largest n value is the 10 to the 6. So we are requiring a n, or at most n log n algorithm for this problem. So the quadratic algorithm is fairly straightforward. So we just try each node. For each node, we root the tree at that node, and then we just compute the weight of the subtree, which can be easily computed using DFS, and find the max value. So what's but when we do this, we are essentially wasting computation here, right? Because we are computing sum of weights of different part of the tree repeatedly again and again, right? So this is a little bit similar to using prefix sum array to try to avoid recomputing. So we can store pre-computed result, then we don't need to computing this again and again. So a linear time algorithm is possible. For every node, if we root this tree at the arbitrary node, then for every node, the biggest edge will be either from this node to its parent, or from this node to each of its children. So then the cost, the traffic that need to go to each of edge to its children is just the size of that children, which can be easily computed. the traffic that need to go through the edge from this node to its parent is the total the total weight for the whole tree, subtracting the weight of the subtree rooted at this node, which can be computed by adding the weight on this node plus all its children. So once we know the total weight in all children, we can compute this easily. So essentially, in one DFS pass, we can actually compute this. So long, assuming we already know the total weight. If we don't, then we need to first compute the total weight and then just traverse the tree again. So let's look at the solution code. So the first the DFS part, computing. So the current node and parent, and go through we are computing the children. So the total weight for the children, and this people array store the this total array store the value that we want to compute. So people array store the value compute. So for example here, so this is a I guess this is already we already read the data. So this is the problem specification is we already have this thing already read. So we are constructing the adjacency list here, and just getting the value for each node, and then we computing the sum. So the variable fence will store the sum, and we do DFS. After DFS, the people value are computed, so we just go through everyone and find out the smallest people value and the index I. So in the DFS, we are computing all the total number of weight for all the children. We do DFS, and then after this DFS called return on the child, we just add that to here, and this value we want to compute will be the maximum of okay. So this is we are keep computing the max. So whether these children, the children of this the total weight for X is we find the biggest value there and assign them to people V, and at the end we will compare with going from this node to its parent, which is total subtract the children of the current node V, subtract the value in the current node V. So that's it.